Hello everyone, and welcome to my channel. This channel is an educational channel where we look at theories of everything, cosmologies, all-encompassing theories, paradigm shifters, and other things that you just might not know about because they're esoteric or obscure, and that you could benefit from learning them. And today is our 381st video on Dewey B. Larson and his reciprocal system of theory. The reciprocal system is a system of theory. So it's like if you learn how the system works, you can apply it in your own life to various situations. Really, any situation. It should be universally applicable. And Larson was an American engineer who lived from 1898 until 1990. And about 1930, he started getting some inklings about his reciprocal system, and he developed his ideas while keeping his day job as an engineer over the next 30 years, and eventually put out his two fundamental postulates about how the universe operates in 1959. And then took those two postulates and through a process of deduction, 165 steps or so, developed his theoretical universe. So this is a universe that comes strictly from his theory. And then in his books, he compared his universe with the empirical universe, measured and observed and documented by the legacy scientists. Now, Larson's postulates, the first postulate being by far more important. And the first postulate is that the universe is composed of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Restated by me, you could say that the universe is not made out of matter, it's not made out of energy, it's not made out of force. The universe is made out of motion, and it's specifically made out of scalar motion, a motion that has a magnitude but has no direction, similar to the dots on an expanding balloon. If you have a balloon with dots on it, you blow up the balloon, all the dots are moving away from each other, but in no specific direction. And so the universe is made out of motion, in particular a scalar motion. And motion is the relationship between space and time. Motion is basically a fraction with time or space as the numerator and space or time as the denominator. And time and space can come in multiple dimensions. So you can have single dimensions like speed, space over time. The bicycle is moving 15 miles per hour, 15 miles of space in 1 hour of time. If you double the speed, you can say the bicycle is now moving 30 miles per hour. Or you can say the bicycle is now moving 15 miles per half hour. That shows you a reciprocal relationship between space and time in motion. You can either multiply the speed, multiply the space, or divide the time. Either one gives you the equivalent result. But you can also have multiple dimensions, such as acceleration. I dropped the ball and it fell at 9.8 meters per second squared. 9.8 meters of space and 1 second squared of time. Space over time squared. And all of our scientific quantities are relationships between space and time, like that. And space and time are, as reciprocals of one another, are identical. They have the same qualities, but they are just in reverse order. Just like the reciprocal of 4 is 1/4, 4 over 1 and 1 over 4. They are the same, but they have their order is different. And they multiply to make 1, like all reciprocals do. So Larson was able to observe that the space was 3-dimensional, XYZ coordinates. We could possibly say 3 or more dimensions, 3 or 4 dimensions. But he said 3. And therefore, time also is 3-dimensional because it has the same qualities as space. The thing that we can tell about time is that it is always progressing. Time is always getting later and later and later and later, but in no specific direction. This is the scalar motion that Larson is referring to, and therefore space has that same quality. Just like the dots on an expanding balloon, space is always getting farther and farther and farther apart. This was actually observed by the legacy scientists with their telescopes, and way back in the 1920s. And they observed that all of the distant galaxies are moving away from each other, but in no specific direction. And, well, that's at least one of the interpretations, because they could also use that to interpret the Big Bang, like that somehow our galaxy is at the center of this and all of the other galaxies are moving away from us. Space and time are also quantized, meaning that there is a minimum unit of space and a minimum unit of time. You have to have a full unit before you have anything. And if you have one full unit of space in one full unit of time, you have the speed of light. And the speed of light is what Larson calls unit speed. 1 over 1 equals 1. And this is the background motion of the universe of motion. In a universe of motion, you always have motion. Motion is omnipresent. There's no place where it isn't. And Larson refers to this as the progression of the natural reference system. You know, an outward motion in space in all directions. And that's occurring at all times. If you have a universe of nothingness, or you observe nothingness, then you still have that that speed outward in all directions. It's some motion that cannot be detected. And he also, it's the state of rest of the universe, the background rotation, the background motion, the ether, the origin, the 0 point. And likewise, with reciprocal system, 1 or unit speed is the center. And so half of the universe is moving faster than the speed of light, and half is moving slower. The half that's moving faster is called the cosmic sector, and the half that's moving slower is called the material sector. The legacy scientists know nothing about the cosmic sector. Einstein said that the speed of light is the maximum speed of the universe, eliminating the cosmic sector from any type of consideration. However, the cosmic sector is identical to the material sector on a general level, except that the relationships between space and time are reversed. So in the material sector, we have coordinate space, 3 dimensions of space, and we have clock time. Time is always getting later and later and later. In the cosmic sector, we have coordinate time, 3 dimensions of stationary time, and clock space. Space is always getting farther and farther and farther apart. So you can see how they're identical, but their time and space roles are reversed. Okay, now today we are looking also then the second postulate of Larson's is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute and its geometry is Euclidean. We will eventually talk about that second postulate. We've talked about it in the past as well. It is not of universal acceptance of some of Larson's revisers, his followers and revisers. But now today we're going to move on to the third installment of reading Larson's article, which is more or less History of Science, called How Much Do We Really Know? And this is kind of a critique of mainstream legacy theoretical science. And he talked about how the really good scientists actually recognize that they don't know what they're talking about. It's mainly like the rank and file scientist who really has an inflated notion of exactly what we really do know. And so when you read textbooks, they say, scientists now know, that's usually not really true. Scientists, the good ones, now accept this particular theory as being the best one available right now, but they don't know it, and they expect it to be replaced relatively soon as they find something better. What they really need is an overarching theory to use as a foundation. However, when such a theory as Larson's appears, they reject it out of hand because they can't understand how all the innovations in science come from outside the field, not from inside the field. And so even though Larson's theory is the answer to their prayers, they don't see it that way because they see it more as a threat to their standing as professors and scientists, and they see it as having to admit that they were wrong about their original theories. And so there's an ego aspect involved that is, basically governing science right now. So anyway, he in the second installment, he talked a little bit about, in particular, the dynamics of stars and how was criticizing the hydrogen to helium star burning hypothesis. And I think that's where we're going to get started right now. Some quite definite evolutionary direction signs are available in the astronomical field itself, but rather than take issue with the physicists, the astronomers have chosen to ignore these signs and to base their ideas as to direction solely on the hypothetical energy generation process. If this process is actually operative, then it necessarily follows that the hot, massive stars, which are radiating enormous amounts of energy, must be comparatively young, as their supply of hydrogen could not maintain this tremendous energy output for more than a relatively short time. But this raises some very difficult questions. As Bart J. Bach states, it is no small matter to accept as proven the conclusion of some of our most conspicuous supergiants like Rigel, were formed so very recently on the cosmic scale of time measurement. And Cecilia Payne-Gaposchkin tells us that the results of age calculations based on this hydrogen conversion process are staggering. However, the astronomers have, almost without exception, shrugged off the contradictory evidence from their own observations and have accepted this product of a hair-raising extrapolation by the physicists as an incontestable fact. Explanations of stellar evolution almost invariably begin with some such statement as this, which introduces Payne-Gaposchkin's discussion of the subject. The problem of the ages of stars and closely interwoven is closely interwoven with the problem of stellar nutrition. A star can shine only so long as hydrogen is available. Or this from Struve. Our new insight into the age of the stars stems from our new knowledge of how these bodies produce their energy. Here is eloquent testimony to the serious consequences or lack of adequate discrimination between factual and non-factual material in present-day scientific practice. The atomic physicists themselves are not deceived. They know that the concept of self-sustaining process of conversion of the stable hydrogen isotope to helium is only a hypothesis, not a fact. And if we read the fine print, we will find them admitting that that is the case. For example, R.E. Marshak, in an article entitled "The Energy of the Stars," makes this statement, quote, so we can safely assume that the stars produce energy by the combinations of light elements through the collisions of their swiftly moving nuclei. And Louis Ridenour sums up Marshak's entire article in these words, quote, as Robert E. Marshak explained in the previous article, there is excellent reason to believe that the energy source of most stars is rather a complicated chain of nuclear transformations whose end result is to form one atom of helium out of 4 atoms of hydrogen. But unfortunately, this concept of energy generation process is not usually presented in its true light as something we can safely assume, or something there is excellent reason to believe. Because of the overwhelming confidence of the physicists in the validity of their hypothesis, a confidence based more on the prestige of the profession than on the merits of the hypothesis itself, there is a general tendency to talk in terms of positive knowledge. And by the time this hypothesis reaches the astronomers, it has become an article of faith against which factual evidence is powerless. As E.J. Opick tells us, this knowledge of the conversion of hydrogen to helium is so well founded that it furnishes a reliable basis for the calculation of time rates of stellar evolution. The highest state to which, that's the end quote, the highest state to which the assumption and belief of the physicists has now risen is all the more remarkable since Opick admits on the very next page that this reliable basis is clearly unreliable. The energy source of the giants remains a puzzle, he says, and hence a more uneasiness may be felt about the application of the theory to the white dwarfs. Otto Struve's confidence in the energy generation process as reflected in the statement previously quoted, is equally remarkable in that it is apparently undisturbed by the fact that this new insight of which he speaks forces him to characterize factual evidence from his own field as apparent defiance of the modern theory of stellar evolution. The damaging effect of these unjustified claims to positive knowledge in basic physics is by no means confined to relatively distant fields such as astronomy. Even physics itself is highly compartmental in present-day practice, and the individual physicists are reluctant to cross boundary lines. Le Prince Renguet describes the situation in these words, quote, "A physicist bears the stamp imposed by the rigid and precise demands of his discipline. At meetings, he rarely comments on anything that lies outside his own well-defined specialty. If the findings of each minuscule, that's the end of the quote, sorry. If the findings of each minuscule division of science are to be accepted without question by the rest of the scientific profession, this merely underlies the necessity of more accurate definition of the true nature of the conclusions that are research, and some measures that will discourage the tendency to say, we know, when the expression should be, we think. Perhaps we have reached the point where we need some interdisciplinary agency to restrain the enthusiasm with which the various specialties overstate the case for the current popular theories in their respective fields. Extrapolations of negative results are not knowledge. In addition to the type of extrapolation which has been discussed, there are also what we may call extrapolations of the negative. Here we find through observation that certain things do not happen in regions directly accessible, like Earth, primarily. We then generalize this observation by extrapolating it to regions that are not accessible, and we say that such things never happen. There is nothing inherently wrong about such an extrapolation or any other type of extrapolation. On the contrary, reasoning from the known to the unknown is sound practice. But it must not be forgotten that an extrapolation of an observed fact is something totally different from the fact itself, and conclusions reached by extrapolation cannot be more than tentative until they are confirmed in some way. A good example of this type of extrapolation is proved by the question of isotopic stability. Under terrestrial conditions, the isotope Fe56, iron 56, is stable. In the absence of any evidence to the contrary, we assume that stability is an inherent property and that Fe56 is always stable. Similarly, we assume that the neutron is always, with one curious exception, unstable, because it is unstable in the region where we can observe it. These are natural and logical assumptions under the circumstances, but they are only assumptions, not established facts. Consequently, they cannot be used to refute any theory which contends that isotopic stability is determined by the environment, and that under appropriate conditions, the neutron may be stable and iron 56 may be unstable. If such a theory is to be attacked, it must be challenged on other grounds. The mere fact that it conflicts with an extrapolation from terrestrial experience is irrelevant, since that extrapolation has no factual standing, regardless of the unanimity with which it is currently accepted. Conclusions based on extrapolation of the negative are not knowledge. Here again, we find the extrapolation serving as the basis for additional conclusions. And again, it should be emphasized that such conclusions are not facts, and they cannot be used in lieu of positive knowledge. Much of the current thinking about the cosmic rays, for instance, follows along lines dictated by the belief that those particles, which are short-lived in the terrestrial environment, are likewise short-lived in interstellar and intergalactic space. The available factual information neither confirms nor denies this assumption. Certainly, the burden of proof rests upon anyone who suggests that isotopic stabilities in free space differ from those which we find in the terrestrial environment. But if any evidence can be produced in support of such a suggestion, there is nothing in the currently available data from experiment or observation that can refute such evidence. The mere fact that practically everyone believes that the stability or lack of stability is inherent does not make this true. Scientific questions cannot be settled by public opinion polls. However numerous its supporters may be, there is still nothing more than a conclusion based on an unsupported extrapolation of the observed facts, and as such, it cannot qualify as knowledge. In this connection, it is interesting to note that current ideas regarding stability are not consistent. The same physicist who reacts violently to the suggestion that stability may be a function of the environment and that his conclusions as to the atom building and similar processes in the extraterrestrial environments may therefore be wide of the mark, does not hesitate to advance exactly the same hypothesis when he finds this necessary in order to fit the theory that normally unstable neutron is a constituent of stable atoms. Okay, we're going to stop it right there and move on to the next section tomorrow. I don't know how long this article is. I think it goes on for a little ways longer, but we'll see. And, you know, he's kind of focusing in on one specific, well, two specific real things here. But I think he's going to spread it out here in the next section. So thanks for tuning in today, and I hope you have a great day.